Hi everyone, how are we doing today? Hope this is coming through loud and clear, and welcome to Paper Free Live. It's been a long road for you guys, a bit longer than advertised due to the whole situation, but let's crack on with this now. I'm going to go through a few things. Some people have asked some questions. There's been a lot of chat, which is really cool. Don't let other people, when you're chatting, get you stressed out and anything like that. This does look like some really useful stuff, but I haven't really had time to look through that. But if you do have any questions at any point during this whole live feed, then hit me up and let me know, and I'll see if I can go through them at the end. I'm not going to go through any of the AQA modules options, so if you're after that, I'm really sorry, but that's just I'm not going to be able to help you with that. I've never taught them and probably going to confuse you, but something that I haven't prepared. There's a few things I'm going to go through. I'm going to give you some tips. I'm going to give you some general points. There's loads of stuff, guys, for you to look at already on my channel, and I'll just pick that up. I'll just ping that up just now if you like, because I know that some of you are looking for these things. There is, if you just go onto my channel and use the little search button up here, little search function up here, and you just go paper free, or you just put Gorilla Physics paper free, and you'll find this type of thing. Here's some really useful things in here. How to, last year's live feeds, how to prepare for paper free. We cracked the exam board secret code is a bit clickbaity. We were joking in my class then, let's have some clickbaity titles, but actually there's some really useful stuff in there. That is the secret to paper free, and it's all about how you actually decode the questions and everything like that. I've got all the OCR A-level pags in one video. I've got all the AQA A-level pags in required practicals. I've got all the Edexcel core practicals. I've got paper free A-level physics a day before. Watch these. There's loads of stuff here, and as you know from my previous ones, I'm suggesting you keep it quite chill the night before the exam. Now it's almost 8 o'clock, so you should be drawing to the end of any kind of stressful stuff that you do, and you should be really looking at just picking up a few kind of key points, just gently going over things, not stressing out, and making sure you go down the quite chilled revision avenue this evening. Okay, so cool. Make sure you get yourself to bed at 10, no later than 10 tonight. There's just a few more. This is the video look just here, and that's about it for all this, all the AQA ones, all the Edexcel ones as well. Lots of feedback. There's full papers as well for paper free. Dr. Lemon's trick to A-level paper free is a really popular one, and that's just about knowing what you're really being asked. So there's loads of stuff on there. Go for that. I was just laughing there because Nick just says RTFQ is my absolute nemesis. Read the full question is what that means, of course, and reading the full question is such an important part of paper free. I think this is an important one for relaxing a little bit, getting yourself a bit thinking through really carefully what the question is asking you to do, and not getting put off. Okay, really important thing. Do not get put off by the context. That's a super important thing. Now, this is the one time it's worth actually trying to do a little bit of a prediction, but not from last year, but from the last 3 papers. So think to yourself, what's been going on actually? What's been going on in the last few papers? If they've done a massive question on waves, they're unlikely to do another massive question on a wave experiment, right? So you can really just check that what's come up so far compared to what's likely to come up this time. If they've actually done a big question on a topic, then probably they're not going to do that again. So it's worth you in your chat, if you're AQA talking about that, if you're OCR talking about that, what's come up, and just making sure that you're ready to go. Now look out for synoptic links, because whichever paper you're doing, this is where the majority of the synoptic paper is going to come from. So one thing to do, for example, which might be quite a nice relaxed thing to do to look through this evening, is just go through your textbook, and they often have like synoptic links or links to other parts of the syllabus. They are really good points just to look for. They could link this to that, they could link circular to this. In fact, circular motion is a really common synoptic link in all papers, right? So there's a tip there. Look at also the links they've made in past papers. So if you want to go through some past paper stuff tonight, you don't have to necessarily go through and do all of the questions, but a nice thing to do, we go through, look, they've linked that to that, they've linked this to that, and actually just build up a kind of idea in your head of what they link and what the kind of common links can be. And I'm going to go through a few today. Also learn the laws and principles. So one of the videos that I just showed there on my channel was actually laws and principles in A-level physics, because a lot of the a lot of the stuff a lot of the questions they like to ask are based around the laws and principles. Here it is, laws and principles of A-level physics, this one here. It's a really good video where I just go through all of the laws and principles that can come up in A-level physics, so definitely check that one out. And another good tip that I like is to annotate an equation sheet. So you have your equation sheet with you and use it almost like a map, right? Actually, if you annotate on it, all right, that is Newton's laws, that is this part, that is this thing, you know, and that's when you use it, then you can have that kind of document in front of you that can remind you of those links that you've gone through and identified tonight. Okay, so I think that's a really useful thing to do. Okay, let's crack on with it. I've mentioned all the practicals videos, so I have all the practicals videos where I just run through all of the practicals in OCR, which are the same for A and B, AQA and for Edexcel. All right, let's crack on. So this, somebody asked me for this, how to do compound uncertainties, right? How to do compound uncertainties is, just one second, excuse me. How to do compound uncertainties is a really important idea. So you've got, let's say they've given you some data and they give it to you in a question. Obviously the mass is 5.0 plus or minus 0.1 kilograms. The acceleration is 10 plus or minus 0.5 meters per second squared. Now when you want to actually calculate that, you want to first of all think to yourself, well, what's the uncertainty in the answer going to be? What's the uncertainty in force going to be? Well, you can't just add 0.1 to 0.5 and think that's going to be the uncertainty in the force, because you're doing something with it. You're multiplying together, so you've got to compound them. So what you need to do is you need to use your general formula. I'll do the general formula of an uncertainty up here. The percentage uncertainty is the difference in the measure, the uncertainty, over the measure itself, over the value, times by 100. And you can kind of put that in brackets because it's a percent, right? So yes, absolutely, lots of people struggle, and that's a really core principle, that idea of uncertainties, and we'll talk about that in a moment. So then what you need to do now is you need to work out your percentage uncertainty in mass and your percentage uncertainty in acceleration. So let's just do that. 0.1, that's the delta x there, or delta m, over 5. 0.1 over 5 gives you 1/50th or 2%, and then 10, the uncertainty in acceleration, 0.5 over 10. Okay, and you know, even though these are easy sums to do, you should still go ahead and do them in a calculator, because guess what, your calculator makes less errors than you do, and also it saves you the brain power for the actual hard bits, right? And now you can actually do your F equals ma, your simple stuff. You can do your 5.0 times 10, which is 50. Okay, and then you can work out what your uncertainty is by adding together the percentages. So your uncertainty, your percentage uncertainty of force, is actually this plus this. Okay, so it's actually 7%. So your final answer that you're going to give is you're going to give force equals 50 plus or minus, well, what's 7% of 50? 0.07 times 50, 3.5. Okay, does that make sense? So that makes sense to you all. So whenever you're compounding uncertainties, you need to add the percentages, not the actual uncertainties. Now that's also the case if you need to square something. Okay, squaring is just like compounding something. So first of all, the percentage uncertainty of current, 0.05 over 6. Gives you, well, 0.8%. And somebody be doing these as well to check that I'm getting these right, because you can easily make mistakes. And this one would be like 2.2%. Okay, so total percentage uncertainty in power of, well, twice the current, so 1.6, because you've squared the current, so it's like using it twice the current, 1.6% plus 2.2 gives you, whatever that is, 3.8%. So then you do I squared R, so 6 squared times 22 gives you 792. And then you're going to just quote that. Your power is 792 plus or minus 3.8% of that. 30, which is watts. Okay, I hope that makes sense. You know, that is a really key idea. Now, whenever you're later on you're evaluating your methods, okay, always be thinking about the idea of percentage uncertainty. Always be thinking about the idea of how can you change this value to be more accurate. How can you reduce that value? What can you do to reduce that value? Well, you can do two things. You can make the actual uncertainty as small as possible, and there are ways to do that, different ways for different measures, or you can make the value you're measuring as large as possible. So make the actual uncertainty small, usually by either having a smaller scale division or repeating and calculating average if it's a random error that you're dealing with. Make that as small as possible, and you make this as large as possible, the actual value you're measuring. So if you can in your experiment, you increase the size of the thing. All right, I hope that was helpful. That's dealing with compound uncertainties. So now I've got 3 common links here. I'm just going to sort of whiz through here. I'm not going to do too much on them, but I'm just going to sort of point out some common links, and then I want you to spend a bit of time this evening actually looking through and thinking for yourself, based on what's likely to come up, what are the common links. So this is the idea of the stop-in voltage practical. So this is the photocell. So what you have is you have light incident on a metal plate, and you actually get electrons given off, photoelectrons, and they move across. They move across to the other side, okay, and you get all these electrons flowing across here. So my point here, I'm not going to go into this in massive detail, but let's think about the link that they could do. They could do the link between quantum and the transport equation. So they could talk about the kinetic energy of those particles. They could talk about the number of those particles coming across. There's loads of different aspects of quantum they could do. They could actually make this part of the, well, it would very likely would be HF equals phi plus a half mv squared max, you know, and they could link that into INOVE, which is the transport equation. You know, they could ask you to maybe work out the speed of these things, hence work out the number of charge carriers, you know, the area of the thing, the measured current. There are loads of different ideas that you can do there. Okay, I hope that's a useful kind of idea. That's just one suggested idea. That's not necessarily likely to be the idea. Maybe as you are chatting, I can see what you're talking about. Basically, you're talking about what might come up. Yeah, so for example, I think the internal resistance might come up in AQA. Yeah, and so you can think about maybe the link with that internal resistance to other things. You can go through my live feeds about the different practicals, and you can look out for that one. You can think exactly, you can look at that and think exactly how, you know, exactly how you improve that practical, so you're ready to go with the improvements for that one. Another common link is the idea of the magnetic force on a charged particle moving through a field. So B is the field strength, and link it to circular motion. So let's say we've drawn a charged particle here. First of all, let's say we wanted to work out what the charge was on the particle, whether it's positive or negative. Well, we know that in circular motion, there's always going to be a force towards the center of the circle to make it kind of accelerate in that circle. So you're going to use your left hand rule. Your first finger field is pointing down into the page there. The cross means into the page, and you're going to orientate your thumb so that it's such that it's pointed into the center of the circle, and then you can see that means negative. So the current is flowing that way, so that must be a negative particle. Okay, I hope that makes sense. That's the first kind of idea there. But then also they can actually use this idea to get to this equation here. So if you say, well, I know that the force on a charged particle moving in a field is VQV. We know that that is a electron, so we can replace the E with the Q with an E. That's the charge on an electron is E, the electronic charge. And we can say, well, it's moving in a circle, so we also know that it's got to be a centripetal force, so we've got mv squared over r to be a centripetal force. You're just making those two equations equal to each other. Nicer pen. Okay, and then you're just going to rearrange a little bit, and see what you can replace. Well, you've got v squared, haven't you? So one thing you could replace, for example, would be you could actually sub in half mv squared here. So you end up then with times both sides by half and substitute mv squared then for ek. So you end up with kinetic energy. Okay, and well, what's the kinetic energy on this charged particle? It's in the electron volt. It's the charge, the electronic charge multiplied by the potential difference. So maybe you could substitute that in for the ek. So you get ev over r equals bev, half bev I should put, and then you can multiply through by 2 and r to move it, and you end up with that thing there. So 2 ev equals bev r. Okay, so that's just one example of how you can combine circular motion. As I said, that's a really common synaptic link, where you actually have mv squared over r gives you the centripetal force, because you know something's moving in a circle. That's a really common link between different areas. All, as is anything to do with energy. So that was actually the link to getting EV into that equation, was actually working through the kinetic energy and knowing that the kinetic energy of a charged particle is EV. Okay, so that's that next link. Stars and nuclear physics. I'm not going to do much actual maths or algebra on this, but just to talk about that, that's a kind of common one. Obviously what's going on in a star is lots and lots of nuclear fusion, so maybe they could give you a nuclear fusion equation excuse me, and ask you to work out the energy liberated by doing that, and then ask you to, based on the power output of the star, and bringing in maybe something about Stefan's law and things like that, luminosity of the star, actually work out how many fusions are going on per second, etc. And I will say also that idea of a per second also tricks people up quite a lot. Another one that comes up quite a lot in terms of synoptic links is potential dividers in this equation here. If there's anything to do with electricity, always be thinking potential dividers could come up in that kind of thing there as well. So I hope that was okay. I hope that was useful. I'm kind of, not going to do too much more, but if you've got any questions, then do. If there's any kind of links that you kind of got here, then do chuck them there. But I want to just talk about this. I talked about this in the first of these 3 live streams. This little bit of advice for all questions: you start by decoding, and then you plan, and then you answer and you check. And the decode step is especially important for paper 3. Now, the in the trick to paper 3 video that I did a couple of years ago, I think it was last year, I can't remember exactly when it was, is a really good one, a really good run through of lots of examples of times when they're giving you a difficult question, a difficult context, but actually the question is really easy. And the joke was that Dr. Lemon, it should be Lemon, sorry, Dr. Lemon, his trick was that he was very good at spotting the actual question, and the thing to decode, the thing that he was good at spotting, was look for the command words. Okay, what are they actually asking you to do? Because very often the first couple of questions, they might give you like a page and a half of actual writing about an experiment that happened 100 years ago and all this stuff, and then the first command word will be define. And that's actually a very easy thing to do, or calculate, and actually there's just a few numbers you need to pick out to get like 2 marks or whatever. So actually sometimes the context can be really, really tricky, but the actual questions themselves are pretty straightforward. And this is what I really think is a super important part of this paper, more than any other, is using that good decode skill, actually reading really carefully, but looking out for what you're expected to do with the information. And personally, I don't read the context until I've read the command words and I've figured out what do I need to do with this information. Okay. And saying that and carrying on, knowing the format of the exam is really, really important. So for example, I know for like Edexcel papers, I know them really like the back of my hand. I know there's always going to be an 8 or 9 mark data analysis question. It's going to be power law or exponential law, and it's going to give you an example of an equation that you've probably never seen before, and it's going to give you some data, and you need to work out from the equation whether it's a power law or an exponential law. And if it's an exponential, you plot a log versus whatever the x is graph. If it's a power law, you plot a log graph. and then you just need to make sure that you know how the mark scheme's written. So for example, you do the data analysis, that's fine, but if you get the wrong number of significant figures, then you lose that easy mark. So you need to have the same number of significant figures as the data that was given to you. You know, these are the, if you know that about the mark scheme, doesn't matter what equation it is, it's just going through the same process. And I do this in detail in some of those other paper 3 videos. And if you know that the first questions are always like, you know, spot whatever the students made with their data or anything like that, then you know the type of format of the question that's going to come up. Also, any longer ones, this is especially important, but any question, think before you write. Do not just go cracking in and started waffling on and filling up half the page and wasting half your time before you've even stopped to really consider what the question's about. That's a really common thing. You know, think what part of the syllabus is this question about before you write. And then answer, then actually do the writing. But because you've had the time to think first, you're going to be able to upgrade your language. You're going to be able to check yourself as you go. And lastly, check your answer and check back with the question. Check back with the command words. Okay, check back that you've done everything you've been told to do. These are super important things. Okay, so I'm not going to be too much longer, but there's a couple more things that I've been asked to go through. The idea of dealing with systematic versus random errors. So these are the two kind of families of errors, right? Systematic versus random. So this is the big thing for you to decode. If you're asked to improve a practical, think first, is this a systematic error or is this a random error? Okay, now if what's happening is a systematic error, then no amount of repeating or taking averages or getting rid of anomalies is going to make you closer to what you're going to be. So an example of a systematic might be a 0, or it might be you know, something like there's more energy being transferred to the surroundings, something that changes all the results by the same factor, either too big, too small. Okay, it doesn't need to be necessarily like the same like multiplication factor, but change all the results in the same way. And a random error, okay, is sometimes big, sometimes small. So it can be either side. Now, the random error is where you do your repeats, you eliminate anomalies, and you calculate a mean average, right? Okay, so if you recognize it's a random error, then it's completely valid to say do more repeats, eliminate anomalies, and calculate a mean. That will get you that'll be worth 2 marks probably, right? Whereas a systematic error, any amount of repeats won't get you closer to the true value, and that's what accuracy is. So you have to change something about the method or the apparatus or the way you analyze maybe. But importantly, you have to change the system. Otherwise, you'll keep getting the same error over and over again. Okay, I hope that's a helpful idea. Just really think about errors being in those two families of error. Some are systematic and some are random. Okay. And lastly, before I take just any questions, any random questions, and then I'll say good night to you all and hope it goes well. And I really do hope it goes well. It's been a long road for you, as I said at the start, but you'll be absolutely fine. So when they ask you to evaluate or improve or suggest what a student has done wrong, think very carefully about these two things again. Is it the results or is it the method that you are asked to evaluate and improve? So very often they'll give you a table of results and they'll say, what thing has the student done when they're recording their results? What have they done wrong when they're recording their results? So it might be number of sig figs. They might have miscalculated a mean. Yeah, they might have not written down all their raw results. There's quite a few different things that it can be, but basically, are you evaluating the results, the recording of the results, the things they've done, the number of repeats they've done? Okay, or haven't ignored anomalies. There's probably more. Any more suggestions for this? and or are you evaluating the method? So that'll be things that actually in the system. Have they not used a fiducial marker? Have they got parallax error? Yeah, do you follow me? So what have they actually done? Have they used too low resolution? Yeah, so for example, using calipers rather than micrometers, things like that. So those are the improvements that you can do if you're asked to evaluate the method. Okay, and you're going to get that by looking and really carefully decoding and just thinking to yourself, and it will be obvious if you actually think through it and you're looking out for, all right, am I talking about the results? Am I talking about the actual thing they've done? Or am I talking about the method? Yeah, calibration was a good one as well. Yeah. Okay. That's me pretty much, guys. Okay. I've got a blank sheet here. If you've got any questions, really quickly, let's just have a little scan through. Oh, how to use a micrometer? Somebody did ask me for that. Okay. I haven't got any like pictures of them, but I'll try my best. So the vernier scale and the micrometer. So let's just do this quickly. Okay, if this is a vernier scale, first of all, right? Let's say these are every half. Okay, and the vernier scale like has 9 little digits. That's just 10, but those 10 take up 1.1 of a millimeter less than a full 10. So what you do is you read off where the 0 is. Okay, so this would become 0 point. And this is in millimeters, and whatever one of these next ones lines up, which looks like it's the 1, 2, 3, 4, 5, 6th one, 0.6 millimeters, that would be reading. So you use on a vernier scale, you use the very first mark to give you the first digit, the whole numbers of millimeters, and it's a little bit further than the first whole number of millimeters. So the second one comes from whichever one of the 10 vernier marks lines up. Okay, now a micrometer has two things going on. It has the values on the drum. The values on the so what we're going to call this. This is the drum and this is the barrel. The values on the barrel, and they are typically whole millimeters and then half millimeters underneath. There's a little line through the middle. So what you do is you look where the drum is passed, and that gives you your first number. So where the drum is passed. And then your decimal comes from the values on the drum. Now, but the values on the drum only go up to 50, so that's why you have to have the half millimeter markings on the bottom. So it might be if it's past the half millimeter marking, and this looks like it's going to become 10. Probably past the next half millimeter marking, so you're going to have to add 50 to whatever this is. So let's say this had lined up at 35 and it was past the half millimeter marking, then it would become 50 plus 35, so it'd be 0.85 millimeters. Okay, and this is one example. How can you reduce the percentage uncertainty? Do you remember that if you're measuring a length? Okay, well, there's two ways you can reduce the percentage uncertainty. You can make the uncertainty smaller. So the uncertainty with a vernier scale is 0.1 millimeter, or with a micrometer, 0.01 millimeter, and then this is the actual value that you're measuring. And wouldn't it be great if you could measure this whole value? Wouldn't it be great if you could measure any value as big as you like with a micrometer, and you could always have a really tiny percentage uncertainty? But remember, the micrometer measures values that are less than 2.5 centimeters, and vernier vernier scales measure less than sort of 15 centimeters. So in that kind of order of magnitude, maybe even 10. So it's important that you pick appropriate instruments for the size of what you're measuring. If it's going to be over 20 meters, then you're going to need to use, or it's going to be over a meter, sorry, you're going to need to use a tape measure. If it's going to be over 30 centimeters, then you're going to need to use a meter rule. You know, these are appropriate readings. We want our percentage uncertainty, remember, to be as low as possible. So always be thinking, and definitely if you look at this, when you're evaluating the method, how can you improve this? Keep your percentage uncertainty as low as possible. That's what you need to be doing to get inaccurate. Right, any other things? Which core practical do you think we could come up? Guys, I really haven't looked at any of the papers because I haven't had access to them. So, nobody at my school's done a resit, so I haven't seen any of the papers. So it'd be wrong for me to try and predict for you guys what you think. So sorry about that. I haven't seen OCR, I haven't seen Edexcel. They haven't asked us of a derivation yet, so kinetic theory potentially, yeah, good stuff. Yeah, I've done the whole kinetic theory. I'm not going to get into that right now, but that's a good one. Official JB, good example of what might come up there. Done the micrometer. Yeah, 15 second YouTube video how to use a micrometer, and I've just taken a little while. It is Mr. Gorilla, that's my name. I often get called Sir Gorilla. Thanks, Mantager, that's cool. That's nice of you to say that. Right, okay, EMF for maximum search coil. Book says when it's parallel field lines, but online it says perpendicular. Yeah, it will be. What you do with a search coil, one way you can do it with a search coil is you rotate it through 90 degrees. So you're changing the flux by rotating it. So you get 0 flux when it is parallel to the lines, and then into 90 degrees you get, well, the maximum flux for that linkage. So you rotate it and you get a change that's through sine 90, essentially from 0 to 90. Sine 0 to sine 90. That was the question about the search coil. There probably will be a 6 marker tomorrow, Debs. Yeah, random is unpredictable. Yeah, so a nice way to sum up that. So systematic error you can predict it's always going to be, systematic error you can predict it's always going to be the same way, whereas random error, it's random, it could be unpredictable, it's either way. Alright, thanks then everybody. I hope you have a good day tomorrow. Let me know how it goes. I'll just pop up tomorrow just with a comment probably, and it will just say something like, how'd it go today? And I really hope that it goes well. You'll be absolutely fine. You don't need to worry about it, okay? Hopefully you guys have got your plans anyway. Hopefully everything's okay. Just go ahead and do your very best, okay? Thanks for the help, amen. Yeah, found you recently, been good content, glad. Yeah, no worries, Zach, my pleasure, buddy. PTR, thanks, mate. Yeah, A-Level Physics Online is absolutely really high quality. You should definitely ask your school to get it if you are, I know you're finished now. Thanks, young filmmaker, nice to chat to you as well, buddy. Yeah, great. Oh, nice, that's really cool. Yeah, thanks, Matt. All right, well done, buddy. Okay, thanks all so much then. Yeah, just let your teachers and things know that you liked it as well. Yeah, Theodore, all right, I'm getting on it, mate. They'll be ready for your feedback after half term, mate. Okay, thanks a lot for the help. Yeah, all right. All the best then. Do your best. Don't worry about it, and then have a good relax until that results day. Well done. Cheers now.